Hello and welcome to the 22nd lecture in this series. In the last lecture, I discussed the inverse function theorem and the constant rank theorem in the setting of manifolds, and I ended the lecture by giving an example of a local diffeomorphism which is not a diffeomorphism. So let me give an example of an immersion now. So I'll take an immersion of R2 and R3. A trivial immersion would be just the inclusion map, xy going to xy comma 0, for instance. But something more interesting is the following. I'll define f of xy is equal to 2 plus cos x cos y 2 plus cos x sin y, and finally sin x. Now one can check that as x and y vary over all possible values, the locus of these coordinates in R3 is precisely, so if I draw this is the x, y, z axis, this is the point 2 and the circle of radius 1. If I rotate this circle about the z axis, well, I'll get a surface of revolution, and that is precisely the image of f. And it is also, so let me first just say the image of f is the surface of revolution in R3 obtained by rotating the curve, instead of saying the curve, let me say the circle, obtained by rotating the circle. Circle is y minus 2 squared plus z squared equal to 1. Obtaining the circle about the z axis. One can check that DFP has rank 2 at all P in R2. So as before, one can just write down the Jacobian matrix and check that it has rank 2. Well, the interesting thing is that so this surface of revolution, I'll just remark that one can also check that image of f which is this surface of revolution is actually just the two-dimensional torus which defined as a product manifold. And so here, so is homeomorphic to S1 cross S1. Right. And as it turns out, as we are soon going to see, this is this image of F is what is called a submanifold of R3. In particular, it's not just a topological space, it is itself a smooth manifold. So once we have that, we can make a stronger statement that the image of F is actually diffeomorphic to S1 cross S1, where S1 cross S1 already we know that it is a smooth manifold because of the product differentiable structure. Right. So now let's move on to a discussion of submanifolds. I will be focusing only on one. There are essentially two classes of submanifolds one studies: immersed submanifolds and embedded submanifolds. I'll focus only on embedded submanifold. So let me define what an embedded submanifold. A subset. So I start with a smooth N manifold. A subset S of M is a k-dimensional submanifold of M So this, as I said, what I call a submanifold in text, also known as, so in standard text they are also called as regular or embedded submanifold. If the following holds. The idea behind this, the definition I'm about to make, is that is very simple actually. So not only should the subset S be a k-dimensional manifold by itself, the point is that it should be a submanifold. So in some sense, the charts that we obtain on S should be related to the charts on M. Now, the prototype for a submanifold, the simplest after all, what is a manifold? Manifold locally looks like an open set in Rn. So now inside Rn, the simplest submanifold, whatever definition of submanifold one takes, the simplest submanifold one can think of as just the k-dimensional Rk sitting inside Rn. So we want to model this on that simple setting. So let's phrase it like this. If the following holds: for every, instead of saying for every, I'll put it like this. If P belongs to S, there is a chart U phi. There's a chart U phi containing P such that phi of U is an open subset of Rk. This K is that same k-dimensional submanifold. phi of u is an open subset of Rk contained in Rn. So Rk contained in Rn by this we mean Rk, strictly speaking, Rk has only k coordinates, while here we need n coordinates. But this we think of Rk as set of all x1, xk, and the last n minus k coordinates 0. So right. So this is the definition of a Kedem. So what we are saying pictorially, this is my M. For instance, let's think of a three-dimensional submanifold, a three-dimensional manifold M, and let's look at S. Let's see what a two-dimensional submanifold of a three-dimensional manifold looks like. So S is supposed to be two-dimensional. What we want is every point P in S, there should be a chart. This chart U phi is obviously with reference to M, since there's only M is all that we have to start with. So this is a chart which will which contains P, and what this chart does, so here I'll draw this map phi. So this U is going to something which I've been calling U1, and this is an R3. Now, sorry, I forgot one crucial thing here. Phi of U intersection S. That's the important thing. So now this is in R3, and what we want is that this intersection here, U intersection S, let me show this here. This blue part is U intersection S. The entire red thing will go to some U1 in R3, and the blue part we demand that it goes inside R2 sitting inside R3. In other words, a Z coordinate should be 0. So it will be in the XY plane. So this phi of U intersection U intersection S, and this we want it to be contained in R2 equal to XY plane in R3. And it should be an open subset of the XY plane. So as I said, the reasoning behind this definition is very simple. It's just that the simplest manifold submanifold, one can even without formally defining a submanifold, the simplest thing one would like to have is the case of, for example, in this setting, R2 sitting inside R3 should be a submanifold, and we want to have the same situation for a manifold. So we just demand that the chart map replicates this picture inside the manifold. Right. That is a embedded submanifold. Well, as I've defined it, it's just a subset with this property. Now there are several things to check. One is that, well, to begin with, it is actually a manifold by itself. So for that, I need charts on S. So first, let's give this charts of this type a name. A chart U phi on M with this property is called, this property meaning, of course, that phi of U intersection S is an open subset of Rk. With this property is called a slice chart for S. Now, right. So first thing to note is that proposition S is a k-dimensional manifold. With an atlas given by, you just look at U intersection S and then phi U intersection S overall, where U phi is a slice chart. Chart on M. Is a slice chart. Right. So essentially, we cover this submanifold, the set S, by sets of the form U intersection S, and we use the same homeomorphism phi which was there on M, but we just restrict it to U intersection S. And the claim is that this provides a this smooth structure, a differentiable structure. In other words, charts on S with smooth transition functions. So one can check point set by general considerations. I won't go over that. Point set topology implies that the subspace topology on S is Hausdorff and second countable. What I want to, so this is not an issue. What we have to just check is that, first of all, that remember that to check that something is a smooth manifold, I have to check that apart from the topological condition, I need to know, I need to have charts in the sense of homeomorphisms. Then I want to check that the transition functions are smooth. Well, so this is the first thing. Since phi from U to U1 is a homeomorphism, phi of U restricted to S, U intersection S, to phi of. So if I have a homeomorphism and if I restrict it to a subset, it will be a homeomorphism of the subset with the subspace topology onto its image. That's all that I'm saying here. This is a homeomorphism, but that's not saying anything much. The point is that since it's a slice chart, this is onto an open subset. This is the main thing. So this is an open subset of RK. Open subset of RK. This is onto an open subset of RK, and then the transition, as for the transition maps, so let's take two such charts which intersect. Suppose if suppose U alpha intersection S, this is one chart, U beta intersection S is not empty. Then, of course, we can forget about S and conclude that U alpha intersection U beta is not empty. And let's just look at the bigger chart. So the picture is like this. So right. So this is, and there's phi alpha here, phi beta, U alpha, U beta. Now we know that this, when I do phi alpha inverse and then do phi beta, which is a map from phi alpha U alpha intersection U beta to phi beta U alpha intersection U beta. For the moment, if I forget about this blue portion, I know that this bigger chart transition function is smooth. And once this is smooth, these are open subsets of Rn. So this is non-empty, and hence phi beta composed with phi alpha inverse is smooth. So what we have is, we have a smooth map, hence we have a smooth map between open subsets of Rn, and what do we want to know? Well, now we bring the blue part into the picture. So in other words, intersect with S. So we want to know if this new transition maps. So again, I have to put U alpha intersect U beta intersection S composed with phi alpha U alpha intersection S. This inverse everywhere just intersect with. So we are interested in knowing whether this map is smooth, knowing that the bigger map is smooth, the map between the smaller subset. So this actually, let me use the blue part. It will show this very clearly. So I know that this overall map, transition map from here to here is smooth, I want to know when restricted to this blue part, it's smooth. So the situation is, hence we have a smooth map between open subsets of Rn, and we would like to know if the restriction of this map to Rk is smooth. This is of course true. I mean, after all, what are we saying here? So for the moment, let's just forget open subsets. That just adds to notational complexity. So let's look at this more general situation. So I have f from Rn. Actually, I don't even need the same dimension, Rn to Rk, Rn to Rm. If f from this to this is smooth, then f restricted to Rk from Rk to Rn is also smooth. And one easy way of seeing is, well, our definition of smooth just is that all partial derivatives so for instance here we know that all partial derivatives of all orders with respect to all variables exist. Here what we are saying is that when I restrict it to this, all partial derivatives with respect to the first k variables should exist and should exist. That's it. That is of course true. This is the second statement is a much weaker part of the first statement. So this is certainly true because the second condition is that partial derivatives of the components of f should all partial derivatives should exist with respect to the first k variables x1, xk. The hypothesis that all with respect to all the variables, all partial derivatives exist. Here it's just for first k variables. So that's it. So the smoothness of transition functions is immediate. All right, so let's stop here. Next I'll talk about tangent spaces to submanifolds and give a theorem generating in a very easy way we can come up with lots of submanifolds. All right, thanks.